Okay. Yes, let's continue with the project description. You can see here, um, we have three options here in terms of project. Option one, at the end of each chapter in the textbook, you can find a section titled Projects. Form a team with at least one other classmate and complete any three projects. And then it's desirable that the projects selected are from different chapters and use three different mathematical modeling methods. It is also highly desirable that you select one from the first five, one from chapter 6 to 10, and one from chapter 11 onward. So bonus points will be awarded for projects that go beyond the scope of the initial description. To qualify to be, please be specific in your final report and final presentation as to the extension of your team implemented. So that's option one. So in the textbook, there is a section called projects. Majority of them are a little bit more than the homework problem. So it's just a little bit extension beyond the homework problem. That's one option. Option two, select any phenomenal or real-world problem of your choice, apply three mathematical modeling techniques to the problem, and present your findings clearly in your report. Compare the three methods if possible. Apparently, it's still a teamwork project so that you can work on three problem set with another team member. If needed, you can find two team members as well, meaning that three of you working on three mathematical techniques. But I prefer that you have a lot of communication inside the team, even though most probably what ends up happening is each one would be responsible for a specific modeling technique, but I still want you to communicate with the other two so that they can provide insights to give you some idea on how that should be implemented, and you give you some suggestion. Meanwhile, you can understand what others are doing in terms of team on the team, and what other team members are thinking through, how they are thinking through the problem. So as you can see that for all the modeling techniques that we learned so far, for different modelers, most probably you come up with somewhat different solutions. So that's the whole purpose that I want you to work together as a team to come up with some idea on how you model the problem. So option three, select one project from the project section at the end of each chapter, use a method describing the project and two additional mathematical modeling methods. Compare the three methods if possible. So essentially, you already fixed one particular problem, but you just use different other two modeling approach from other chapters. That's a difference between option one and option three. Is option one, you have three different problem using three different methods, but option three is one problem used three different methods. So that's the difference between all of them, among all of them. So in terms of the um, my preference, I hope that you would come up with something that's really useful for your business or for your current work. So option two probably is more preferable, but it doesn't mean that you have to choose option two. You can choose option one and option three, and I'll still treat all the projects fairly in terms of the grading on all different three different options. And then, as I said, it would be a team project. Two of you would work together. Of course, if you need three people, you can just form the team as well as a team of three. Occasionally, some students say that my schedule just doesn't work out with some other students. Then I have to just work on that by myself. Then that's fine as well. But if you're working by yourself, you don't need to finish three problems. You probably need to finish one or one and a half. In that case, uh, that should be sufficient. So we can discuss that. That's a whole purpose for this submission, which is number one, form the team. Number two, come up with some projects that you plan to work together, and I can take a look and we can discuss through email, and then we can finalize your proposal. So here it says, again, I already discussed this. We said that we need to form the team by end of this week, and then proposal draft is due by end of next week. You just need less than 1 page. Please address the problem that your team is trying to solve, and then in the following week of next week, I'll just discuss with you on the project, and then you can finalize it. So potentially, number 2 and number 3, the submission would be the same, but you still need to resubmit number 2 if it ends up that I say, okay, your proposal look fine, the draft look really it's well defined, but you still need to resubmit in the number 3 submission. And then after that, it's already November the 6th. I'm saying that number 4 submission would be a resubmission of number 2, potentially could be the case. And then after that, which is from November 13th all the way through December 14th, in that 1 month time frame, you are basically working on your project. And then because we still have other sessions going on, still have homework in that 1 month time frame, that's why you still need to pay attention to what we learn in class, even though it's not as much work as the beginning of the semester. By then, which is already week 11, we still have 2 or 3 homework, and it's not as much as what we have earlier. So hopefully we'll be able to handle in that 1 month time frame. And then after December 14th, you could take another week to finalize your project report. So your presentation slides really due by December 14th in the presentation, and then potentially we can do the presentation on the 14th. And then let's see if we have enough time to cover everybody. If we do, that would be fine. If not, we will figure out some other time after that, sometime between December 14th and December the 21st. That's pretty much actually the everything. And then at the end is this report. Report is that what I'm kind of expecting is analysis of the problem, methodology you used, details of the methodology, the findings of the project, and are they different from your initial expectation? If so, is there a super explanation? Potentially, you could potentially add what potential you can improve the methodology or the project further for some sort of future work. So that's a snapshot of the project. And then if you take a look at here, look at the schedule, again, form the team by end of this week, and next week you need to submit your project proposal. Any questions on this?
Yeah, I have one question.
Go ahead.
Yeah, so so suppose we just want to do like 3 projects from the textbook. Even then, do we still have to submit a project proposal?
Yes, you need to say which 3 that you identified, and then potentially what's the methodology you are using there.
Yeah, so in the project proposal, I would just have to mention like which 3 projects I choose, right?
Exactly.
And then propose like any extensions.
Yeah, if you have any idea on extension, that would be nice. If not, you can also just say that I'm working on these 3 problems.
That's it?
Yeah, that's it. Yep.
All right. Thank you.
Okay. Any other problems? Any other questions? Okay. So some other logistics, right? So I think we have finished the first 5 weeks homework, and then and you submit 6 and 7, and then this week is week 8. So I think I most probably would be grading one of these 3 by the end of this by next time that we talk. so that you have a better idea on your what you have done there, and then you always have to come back and take a look at the solution and understand all the problem set. I don't think you learn enough if you don't revisit all those topics. Okay, so let's continue with last week. You pretty much actually already probably have read the textbook, but I still want to give you some insights on my understanding of these problems. So the previous section week that what we covered was how to use graphs as models to model model problems, and then how we're going to describing graphs, and then what types of graph models, and then what are the major key graph problems that can be solved using graph models, and then what's the connection between graph models to math programming. And then we can roughly start with the introduction here. Which one? This one particular one is the 7 bridges of the Königsberg problem itself is the starting point of any of the graph theory and graph-related modeling techniques. So essentially, in this example, for example, if we can use those point, in this case we use capitalized word. Hold on, let me get a pen. I'll get a laser pointer. So we use capitalized point in graphs. We call it nodes to represent the nodes of all those bridges. And then, so you can see we have sorry. In this case, what happened is we're using nodes to represent all different areas. This area in the middle is node A, and then the area outside of the city bridge is node C. So similarly, there's a node D and node B, and then which are connected by different bridges. And all these bridges are called edges in graph theory. And the edges are used to connect nodes in this case. And then there's some more technical terms such as incidence. We talk about what's the incidence of a particular node. And then in this case, you can see that all the edges between A and C, there are 2 edges which are C and D, and then between capitalized C and D, those 2 nodes, we have a bridge of G. So that's a graph representation of the physical problem. Let me see if we have some node discussion. Yes, we did. Okay. So and then there's a famous problem that's called graph coloring. And then given a geographic map, it's possible to color it with 4 colors so that any 2 regions that share a common border of length less than 0 are assigned different colors. And then it turned out that this is one of the solutions for the graph coloring problem. So if you use triangle, rectangle, and circle, and star to represent 4 different colors, you can see that this will be a solution that satisfies that need, which says any 2 regions that share a common border are assigned different color. And then how to describe a graph? You can use a vertex set. As we said, all the nodes are considered to be a vertex. And then in this case, if we go back there, we have a vertex set of capitalized A, B, C, and D. And then we have edge set. Edge set would be the lowercase of A, B, C, D, E, F, G. That's the edge set. And then we say incident. We say what is incident of what's the incidence of a particular node, which would be all the edges that's incident from particular node. In this case, if the node C, capitalized C, incidence to C, D, and G edges. And then adjacent. Adjacent, we can talk about adjacent nodes, adjacent vertex, or adjacent vertices, which would be the same thing, all considered to be the adjacent nodes. And then we can talk about adjacent edges as well. And then in this case, we say that capitalized C and D are adjacent vertex. I'm sorry, actually, I don't think there's let me search. I don't want to mislead you. Let me search. I don't know if there's adjacency of edges at all. Hold on. So I used adjacency edges in graph theory, and then apparently it is there's adjacency here. Okay, here is the story. Two vertices are called adjacent if they are connected by edge, but two edges are called incident if they share a vertex. So, so in this case, we see that C and D are incident with each other, and then we actually majority of the time we also say that no edge C and D incident to node C. So that's the adjacency and incident. Beyond that, we have this concept of degree. So how many degrees, how many edges incident to a particular node is considered to be a degree. For example, for this example, for capital node capitalized C, it has degree of 3. C, D, and G edges are connected to node C. That's why it's called a degree of 3. And then edge node A has a degree of 5 because it has A, B, C, D, and E there. That's incident to node A. And then with all this definition, in social network analysis, we have some interesting topics that we can share, we can discuss that would be relevant to some of these definitions. So even though here we didn't actually get a chance to explain that yet, but hopefully after this section of all these lecture notes, let's go to some of the social network analysis related terminology, and then we can quickly go through some of those using what we have studied here as basics fundamentals to understand those social network problems. So graph models, for example, one methodology is fitting a piecewise linear function to the data is a graph way. Potentially, for example, for this problem, you would think that potentially you could fit a piecewise linear in its nature, maybe in its nature, two possibilities, a couple of possibilities that can fit a linear function to the data, right? And then and you can see here possible solutions. It could be this, could be this one, could be the third one. And then we know the second solution have a potential overfitting problem, and the first one potentially is a linear regression solution. And then the third solution could be in between, and then it's a piecewise linear function. It probably fits better than the first solution, not fit as good as the second solution, but the second solution do suffer from the overfitting problem. And then for graph models, we always have graph solution based on cost structure. That is to say that there is a cost between node to a different node. For example, from 1 to 2, there is a cost associated with the edge. Potentially, it could be the travel time. It um, could be the distance. Could be anything that you can use to represent the graph. And then textbook has this example saying that how to use softball example. Suppose that AI A1 is able to play with position 2 and 8, so that we can have a connection between A and 2, A and 8. And then we could also have B0 bow. Bow actually have he can play the position of 157. 157. And then the graph problem for this particular case is really just trying to find a match that best utilize the skill sets of all the players. And then, as you can see, potentially the solution may not be unique if we don't have a cost structure in there. So if in some cases, if we say that okay, L plays 2 better than position 8, then we can use a lower cost between node A and node 2, so that when we try to model the problem itself can be solved using certain cost structure, try to minimize the objective function. We would be able to find a solution that solve the problem in a better way. That's the example of the solvable example matching problem. And then a different problem is called vertex cover problem. We're saying that find a vertex cover that would be able to cover all the edges. And then there's correspondingly there's a problem called minimum vertex covering problem. Find the minimum number of vertices that would be able to cover all the edges. That's the idea for the placing a city problem. I hope that you already read the textbook and then understand what that is. And it's if not, do some more research on your end. But in general, textbook is rather it's self-explanatory in terms of explaining all of these concepts. And then shortest path problem itself is a very famous problem in graph theory. The idea basically is you have this input of a directed graph, and then as you see here, we call it directed graph. You would see that there are many cases there are the undirected graph, or the one direction, in this case, directed graph. So usually we call it directed DAG graph type of graph. We consider it as directed acyclic graph. You don't have any cycles in the graph. It's one of the typical graph modeling problem. And then you're trying to get some, for the shortest path problem, you just look at what's the shortest distance between origin and destination, and the algorithm itself is specifically explained in the textbook on how you can go through each step to see which one is the next move that you should be taking, and then you find the shortest path. And then for maximum flow problem, algorithm is on page 328, and then you have an input, which is a directed graph, and then the output is the maximum flow from the origin S to the destination of T in the graph. I would say that the maximum flow problem is less important than the shortest path problem, which probably worthwhile to go through yourself and then work on some problems yourself. And then there's this bipartite matching problem using maximum flow that is trying to solving a specific problem. Once you already know some sort of algorithm, you're trying to model the problem to a maximum flow problem so that you would be able to solve the bipartite matching problem, which was the same as very similar to what we have started, just took a look on the baseball matching problem. And then you can be translated to a maximum flow problem by adding supplementary edges from the origin and the destination to the players and the positions that they can play. And then you add unit 1 as a cost, you would be able to model that problem as a maximum flow problem. And then a traveling salesman problem itself is saying that we have a origin and then we're trying to travel all the cities with a certain cost. For example, if we start with A, and then we need to go through all the edges, all the nodes, and then come back to A. That's a problem. And then how to model that problem is happen that we have a solution here. Hopefully, hold on, let me go there. No, it's not here. So I really want to show you what's the definition of the um, let me go to the wiki, because unfortunately that textbook itself doesn't have sufficient enough information on the math problem of the traveler salesman problem. So it's heavily used in the vehicle routing problems set, and then it's a difficult problem. And then how we can solve it. And then it can be modeled as an integer linear programming formulation. And then if we assume that xij equal to 1 if the path goes from city I to city j. So in this case, if at the end we choose A to D first, then xad equal to 1. Otherwise, if you don't choose x, ae, for example, then xae equal to 0. So our decision variable is the path goes from city I to city j. Otherwise, 0. And then what we're trying to do, we're trying to say that there is a certain cost associated with traveling from I and J, right? So which is the Cij. So we know that when we travel coming back to the origin, so starting from J equal to 1, and then the point that you are trying to let's think about it this way. Start from this origin at I equal to 0. You're trying to travel all the rest of the j's. J equal to 1 to n, but j is not I. You don't need to stay at the same location, but even though at the end you comes back, right? So that's the idea that you would sum all the costs associated with each step, Cij times Xij, and then sum of them up. That makes sense, right? That's the objective function of the traveler salesman problem, trying to minimize this cost function. And then we see that Xij is between 0 and 1. The reality is really it's either 0 or 1. But because we have some other supplementary constraints that helps us to relax that xij 0 or 1 a little bit, and then we relax it to between 0 and 1. And then see that the next one. Next one says, coming from I equal to 0, going to some other j, which j is not I itself, sum of them equal to 1, meaning that you can only go out from I equal to 0 to one other location, right? Same thing, because this I equal to 0 is generic, right? So saying that if going from C, going to B, XCB, XCA, XCE, XCD, sum them up should be equal to 1. That means you only go out from C once. That's the whole purpose of traveling salesman problem. You go from A, you need to visit each other city only once and then come back to A, right? For a UPS driver. So that's one. And then the second one is coming into the J, a specific node, sum up equal to 1. In this example, if we look at this example again, that says anything coming into C should sum up to 1. That would be sum xdc, xec, xac, and xbc would sum up equal to 1. That's the next function or constraint, we would rather think. And then on top of that, the last function is rather difficult to understand. And then I don't think I would be able to explain clearly at this point of time. But in general, the basic idea is trying to avoid a subtour so that there's no case that what happens that you would visit AEC and then you think that, okay, you visit that of them already, that's you're trying to avoid this subtool, because potentially if you have AEC, you didn't visit B and D yet, but in terms of the linear programming problem, if you don't have that constraint, you potentially the solution would be only that particular solution. So that's the case that we're trying to avoid, and then this constraint is considered to be subtour avoidance constraint. And it has a little bit more information there to discuss. Hopefully you would be able to read it through, and then we can discuss if you actually have some specific questions on this if you're interested. And then you can see that this problem is actually not trivial to solve. People say that it's NP hard. NP hard has a specific definition on the computational time, and then how to solve it. And then here is an example on the wiki to tell you how long it takes, how many evaluation it takes to find the optimal solution, and then whether there is a way to improve the optimal solution. So that's one thing that I actually discussed here. Hope you would be able to get a little bit color on the traveler sales problem. And then we have two more formulations to go through. One of them, it happens to be called the vertex cover. We say that each of the edge, let's go to the, actually let's go to the, wiki as well, look at the vertex cover problem. Okay, so here, let's look at the problem itself first, right? A vertex cover of a graph can also be more simply thought of as a set of S of vertices of graph, such that every edge of that graph has at least one of the member of S as an endpoint. So in this case, for example, the red points would be the solution. All the edges in the graph is incident to one of these red dots, right? Same thing as the second graph, etc., etc. And then mathematically, how we can model it. Let's go back to the slides very quickly. See that we're trying to okay. So here it says that we're trying to minimize this z. Z is a sum of xi if xi is in a vertex cover that we're trying to find. And then if it's not in the vertex cover, then it's 0. So in this case, essentially the red dots at the end would be all the i's that's equal to 1. And then we say that xi and xj larger than equal to 1, meaning that for any I and j belong to the edge in the graph has to be covered so that one of them, xi or xj, one of them has to be picked so that the edge between I and j would be covered. That's a problem for the vertex cover. And then you would say that this problem is actually a linear programming problem, apparently because the object function is linear and the constraints are linear. Some of these look really straightforward when you model it. And the majority of the time what we're facing is really how can you model the problem, come up with the definition of decision variables, come up with the constraints, and then model the problem, and then try to solve it. That's really the art of the part of the art part of the modeling. And then once you have that, sometimes you could also have submodels to predict a specific decision, a specific variable. For example, the right-hand side, instead of larger than or equal to 1, maybe larger than or equal to x, and then try to use some sort of solution prediction methodology to predict that x. That's the whole purpose for the modeling part. So, and then maximum flow is also maximum flow is a math programming problem. Here we use the how to maximize the flow between S and T actually, or S and J, and J is any of the points that connected to downstream of the S. And then one of the constraints here is the first one is called conservation of flow. So anything going to J from all the points, all the i's, should be going out to other places from J. That's called conservation of flow, meaning that anything going through a particular node should go out from this node as well. So that's how the first constraint uh, 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 is trying to represent. Saying that, again, all the flow coming from all the i's to J equal to the flow going out of J to all the points connected, all the points that can be considered as K, all the K's that's connected to J. That's the conservation of flow. And then the second is the capacity constraint, because Xij can, on the specific edge, the flow cannot exceed the maximum capacity of the ij. And then Xij has to be larger than 0, and trying to solve this problem itself is also a linear programming problem. Okay, that's pretty much that we want to cover for the network analysis. As I mentioned earlier, we actually want to go a little bit deeper on the social network analysis. So let's spend a little bit of time there as well. It happens that this week the contents are not as much, so we probably won't spend too much time there. So apparently, it is. Oh, you have some question? Go ahead.
No, I was just telling you that we weren't hearing you. You went silent for a second. You're back though.
Okay. Yeah. I was trying to find things. That's why my microphone is not beside me. Okay. Apparently, social network analysis itself is it's subject that has been studied by a lot of social science guys, and then itself is is a well-studied subject. I should say it that way. And on the other end, it does have a connection between social network analysis and the network modeling that we actually just studied just now. So let's quickly take a look. But by no means that I'm trying to tell you what's in the social network analysis, because itself, it could be a subject that takes weeks to study. So I think again, the whole purpose of our course is really just to point you to the right direction on each methodology, and then down the road, either in other courses or in your work, when you come up some of these specific cases, you would be able to use some of the methodology here, not necessarily you already learned, but at least you would be able to do some research on your own down the road. So let's take a look at the social network analysis. What does it do? What does it do? Here it says, okay, it has ties, edges, and links, and nodes. It's the same thing as our network theory. And then just want to see some particular uh, some particular metrics that's commonly used in the network analysis. For example, in the social network analysis, for example, bridge. An individual whose weak ties fill a structure tool providing the only link between two individuals or clusters. That's called a bridge. And then what is a cluster? So potentially you can see that for the graph on the top right, you can see that based on the communication, you would see there are at least 3 clusters in the graph, right? And then if we see that one of the point, in this case, maybe this one would be a bridge between those two. And then some other things such as centrality. Centrality refers to a group of metrics that aims to quantify the importance or influence in a variety of sense of a particular node within a network. In this case, centrality probably more have a higher centrality of some of these nodes in the middle versus some other ones, right? And then density of the graph, and that's actually something that you should look into in the social network analysis. And also things such as clustering, cohesion, the degree to which actors are connected directly to each other by cohesive bonds. Structure cohesion refer to the minimum number of members who, if removed from a group, would disconnect the group. Those are the things that I want to point you to what's out there for social network analysis. And then potentially we could also understand that this is 2012 election to understand the narrative network of US election in 2012. And then one of the famous example in the social network is the Enron dataset. Enron actually, before they actually published their internal email communications after their collapse, or before they collapsed, probably a couple of months email data set. And then that one gives you some study of things in the nature of the relationship between the individuals in the company and the importance of individuals in the particular network. So with that being said, let's take a look at quickly take a look at what it is about. See here says starting with the annual email data made available by this, and people started analyzing it. It's not only social network analysis type of analysis, but also text mining because it's in email data. So let's pick one of these example and then see if there's something interesting we can take a look. Okay, it's an undergraduate research project, and let's say what they did for the annual email data. Look at the email, did some text mining, and then get some topics modeling. It's more text mining apparently, so let's see if we find something interesting on the, no, we don't have social network related study. Okay, here, network analysis with the unrun email corpus. So apparently they define some sort of metrics between the communication between two employees. Centrality and rank, degree, and eigenvector centrality, closeness of the individual relationships, and then the betweenness of the nodes. Some of the metrics, and then let's see. This is some sort of clustering, understand the relationship between all the groups, all the individuals. Measure similarity. Okay. So this is something that I just pointed you to some of the potential analysis that can be done in social network analysis. Unfortunately, it doesn't look like they have a lot of visualization. I'm going to share this to you guys. I think it's somewhat looks like something worthwhile to read if you're interested. Okay, that's pretty much that we're going to cover for the network models, and then we have to go through this week material and doesn't have a lot. And this week we're trying to use probability and expected value and decision trees to evaluate alternative possibilities using expected value to make a decision on certain decisions on different nodes. Then we know that the model could be deterministic, it could be stochastic, and then stochastic involves chance, involves risk. And then in stochastic scenario, we need to use probability, and usually we use expected value to represent the average exposure. So in this case, for example, here expected is W1 times P1, it said plus W2 plus P2 times P2, etc., etc. P is the probability of the event of each individual outcome, and then the sum of the probability should be equal to 1. And then for each outcome, there's an associated payoff, which is W1, W2, etc., etc. And then we can get the expected value of the gain. And then for decision tree, what we're trying to do is, for in this case, okay, if we say that we have at a certain node, first node, we have two possibilities. One possibility is to do a user construction, and then the other possibility is to do a remodel. And then for the new constructions case, this is called a probability node because at this stage, it could be successful, could be unsuccessful, and then associated with the successful case, there's a value associated with this new construction being successful. What's the value that you can get for this project? And then correspondingly, you would get a value for the case that new construction unsuccessful. And then you would have other two cases as well. Remodeling successful. What's the value? What's the output of this path? And then what's the output of the remodel unsuccessful output? So you have put all the different values at the end of each path. So that let's go backtrack. For this particular node, what's the expected value of a new construction? It will be the expected value, a value of the first option times 0.2 plus a value of second option times 0.8. You can get the expected value of a new construction. Similarly, you can get the expected value of the remodeling. And then on top of that, your decision node is really trying to maximize your expected value. So at the end, you would pick which one has a higher expected value, you would pick that one, right? So in many of the cases for venture capitalists, when they want to analyze different scenarios in the future, different cases, they use this type of methodology, which is called decision tree. And remember that in decision trees, you have two types of nodes. One type is called decision node, which is this square. And then second type is called probability node, which would be this circle. And then as you could imagine, the problem could become really complicated. It could have multiple paths, multiple decision nodes, multiple probability nodes in the graph as well. So in this example, sequential decisions and conditional probabilities that actually the textbook explained. If you spin a 1, and then what would you do for different probability, and then what would you do in terms of the decision, and then at the end, the way that we get the expected value is really just more like backward deduction, starting from the end and then get the expected value for this node. For example, you use 10 times 0.25 plus 6 times 0.25 plus 4 times 0.25 plus 0, you get the expected value of this guy, and then you can get this maximum value between those two so that you can make a decision on what you should do here, and then that's the whole idea of these sequential decisions and conditional probability. Go through that example, and then just remember that it's expected value is decision node and probability node, and then you should be able to figure it out. So in other words, in the probability node case, you get the expected value, but in the decision node case, you just need to compare the maximum between those two. Whichever is maximum, you just pick the one that's maximum. And then examples, as we just discussed, it could be new construction versus remodel, could be investment or nature, could be investment strategies. Think about what to do for different scenarios. As I mentioned earlier, for venture capital, they most probably would be using some sort of decision tree to make a decision on whether they should invest on a certain project. That's pretty much actually everything that we are going to cover this week, including graph theory and probability-based modeling decision tree in general. And then just remember that you need to form the teams by the end of the week. I think that someone already initiated a conversation, very good, and very good from that perspective on the blackboard, trying to find teammates from there. I encourage you guys to continue with that conversation and then find your teammate. And then by the end of the week, send me an email stating that, hey, I'm working with Y and Z. Here's our team. And then by end of next week, come up with the idea of what you guys are going to do with the course project. Any questions? No? So if you don't have any questions, we can stop here, and then feel free to send me an email if you have any questions, and then form the team by end of this week. Without further ado, let's just stop here. You all have a good night.